Hi, I'm Julia, and today I'm going to tell you about a decentralized Bayesian algorithm we developed to allow a swarm of robots to make decisions about features of their environment. Let's imagine that you're sending a group of robots to Mars to build a habitat for humans who will come after them. That's a complex set of behaviors that require the robots to make a lot of decisions throughout the process. They start out at some potential habitat location, and they need to move around to evaluate some features of the environment to decide whether it's suitable for a habitat. They might need to start by deciding whether there's enough water or the ground is stable enough. If the criteria are met, they can start building, or if not, they move to a new location. Importantly, making these decisions about these features requires not just that the robots are in some transient consensus, but they have to collectively lock in an irreversible choice. This is a go, no-go decision, and it's a vital component of chaining together collective actions into complex behavior. Our algorithm is designed to let robots make this kind of go, no-go decision. But you can imagine that there's a balance involved in this kind of decision-making. The robots could spend more time observing to make more accurate decisions, but that would slow down their decision-making process. To put it all together, our algorithm is designed to answer this question. How can a group of robots collectively make fast and accurate go, no-go decisions about features of their environment? To answer this, we looked at a simpler model than Martian robots. We used a model problem where a group of robots decided whether or not an arena was filled with mostly black or mostly white squares. The arena has a fill ratio, which is the ratio of the space that's filled with white. If an environment has a fill ratio above 0.5, it's mostly white, and black if it's below 0.5. To go with this minimalist environment, we used a correspondingly simple robot model, the kilobot robots. For this paper, we also conducted all of our experiments in simulation. The kilobots can sense their environment color with an ambient light sensor, but they have no localization, and they move at about 1 body length per second, and they can only communicate low bandwidth messages within about 3 body lengths. They're also sparse relative to the size of the environment, but this setup does let us understand how much we can achieve in a very simple system before we add additional complexity. We solved this problem using a Bayesian approach. You can imagine the arena's fill ratio as the probability of making a white observation like a biased coin flip, which means that we can model this likelihood of observing the color as a Bernoulli distribution. This has a beta distribution as its conjugate prior, which works well for modeling the fill ratio because it's bounded between 0 and 1. Here, the alpha and the beta parameters correspond to the number of black and white observations that a robot has made. Each robot keeps a beta distribution to model the fill ratio of the environment. Over time, as the robots make observations, the posterior will get peakier around the actual fill ratio. To make decisions from this distribution, a robot looks at how much of the posterior probability density function is above or below 0.5, which corresponds to the environment being mostly black or mostly white. When a large enough percentage, say 98%, is on one side of 0.5, the robot makes a decision. That percentage is what we call the credible threshold. Compared to bio-inspired algorithms commonly used in swarm robotics, this provides a statistically grounded framework for decisions. It also gives us tunable parameters, like the parameters of the prior or the credible threshold. This also isn't limited to beta distributions and black and white environments, so we hope that this can be used for a wider variety of go, no-go decisions in the future. Each of the robots in this simulation is running the same algorithm. Throughout the experiment, each robot does a pseudo-random walk. At some time interval, it observes its environment, which will either be a black or a white sample. For every new sample, the robot updates its beta posterior distribution and checks whether that decision criterion is met. Along the entire time, the robots are always broadcasting messages to any nearby robots. They're sending their most recent observation or possibly their decision, which I'll explain in a moment. Any robot that receives these messages will update its posterior just like it's a sample that it observed itself. We implemented and tested our decision-making algorithm in the simulation. We put 100 simulated kilobots in a 2.4 by 2.4 meter environment and ran a sweep over 5 different parameters. The first parameter we varied was the use of positive feedback. I said before that they would either transmit their observation or their decision. When we used positive feedback, robots that had already made a decision will always send the value of their decision in place of the observation. We expect that this will reinforce the decisions of robots that decide early, which may either split the decisions of the group or push everyone toward consensus. Next, we varied the observation interval from 1 to 300 seconds, which is how long the robots walked around between taking samples of the environment. A short interval means more observations, but they will be highly spatially correlated. On the other end, you could have fewer observations, but they'll be more representative of the environment. Next, we also varied the credible threshold. If you pick a larger threshold, robots need more observations and therefore more time to make decisions. We also changed the prior that each robot started with at the beginning of the experiments. A larger, peakier prior around 0.5 does mean that the robots will take longer to make decisions because they need more observations to shift the probability mass away from the middle. Finally, we tested the algorithm across different environments, from fill ratios of 52% white to 80% white. Environments that are closer to 50-50 will be harder to distinguish, which also makes them the most interesting. So today I'll just be showing you the results for the 52% fill ratio, but you can see more in the paper as well. Before we get into the results, I want to show you a video of what this decision-making looks like in the simulator. Here we have 100 robots in an arena with a fill ratio of 0.7. They're color-coded based on their decision state. While they're undecided, they vary from pink to teal based on how much of the probability mass is above 0.5. All the robots start out gray, which means that their probability density function is symmetric. You can see that once the probability reaches a threshold of 0.9, they start to turn green, which means that the robots decided that the environment is mostly white. Then they start transmitting their decision in place of their observation, which influences the posterior of the other robots. In this experiment, you'll see that eventually all of the robots turn green, which means that we got 100% accuracy in the decision-making in this particular trial. To understand the effect of the parameters on the decision speed and accuracy, we treated this as a multi-objective optimization problem. Here you can see the Pareto front for decision time versus decision accuracy. Each individual point on this graph represents 100 trials for a particular set of parameter values, with a shaded ellipse showing the 25th to 75th percentiles along each axis. The positive feedback here in yellow has a very dramatic effect, improving both the speed and the accuracy of the decisions. Since the positive feedback was so effective, let's focus on just the conditions where we use the positive feedback and look at the impact of the interval between observations. We can see that longer intervals between observations in yellow gave consistently higher accuracy. Taking samples more frequently meant they got samples quicker, but since they were so spatially correlated, it meant that the overall decisions were less accurate because they didn't represent the true environment. We can focus on just the cases with longer observation intervals since those perform better, in this case ones with observation intervals over 15 seconds. Now we can see the effect of changing the credible threshold. Using a threshold of 0.99 gives the most accurate results, but it also takes the longest. In some conditions, we can see that a lower credible threshold results in much faster decisions with only a relatively small accuracy cost. To understand this trade-off, let's look at just the conditions where we had a credible threshold of 0.9 on the left and a credible threshold of 0.99 on the right. Using the lower credible threshold can achieve fast, accurate results if you choose a large regularizing prior. If you have a low threshold for making decisions, starting with that peakier prior around 0.5 prevents robots from making premature decisions before they've gotten enough observations to decide accurately. In summary, we've shown a Bayesian algorithm that allows a group of simple simulated robots to make go-no-go decisions about an observed feature of their environment. Even though we didn't make many assumptions about the capabilities of the robots, they're able to make fast, accurate decisions. We found that bio-inspired positive feedback improved both the speed and accuracy of decision-making. Counterintuitively, we found that decision accuracy improved when robots made fewer observations because it reduced the spatial correlation of their samples. We also showed that choosing a prior well lets you use a credible threshold, lower credible threshold to get fast decisions with a minimal cost and accuracy. If you read the paper, which I hope you do, we also show that the algorithm is adaptable to different environment difficulties. In an easier environment, with a fill ratio further from 0.5, the robots make much faster decisions. Finally, the paper also compares this Bayesian algorithm to a benchmark algorithm we developed that provides theoretical accuracy guarantees even in the worst case. In the future, we plan to extend this algorithm to solve a wider variety of environmental perception and decision-making problems. If you recall the Mars example from the beginning of the talk, there are other feature-based decisions you might want to make. For example, where's the best and most reliable water source? Many of these require more complex or more capable robots. Robots with localization could make more informed choices about where to move in the environment and use adaptive sampling algorithms to choose where to sample. We could also improve the usefulness of the messages that the robots communicate. We already showed that using positive feedback can improve decision-making, but could we do even better? With that, I'd like to thank you for watching, and I'd also be happy to answer any questions you have in some digital form. Thanks.